Welcome to this explainer. Today, we're completely unpacking the fascinating journey of supervised machine learning and seeing exactly how raw data transforms into really powerful predictions. Have you ever wondered how your inbox magically knows what's spam and what's a real message? Well, we are going to open up that black box and show you exactly how it's done by tracing the actual journey of the data itself.
Here is our roadmap for today. 1. What is machine learning? 2. Phase 1. Data collection. 3. Phase 2. Data preparation. 4. Phase 3. Model training. 5. Phase 4. Prediction. And finally, 6. Why it works.
What is machine learning? The basics.
So we really need to start at the foundation here. What exactly is this technology everyone keeps talking about? Well, instead of explicitly programming rules, like manually typing out code telling a computer, hey, if you see the word Viagra, flag it as spam, we actually feed the machine a ton of examples. We let it algorithmically build its own statistical model based entirely on that data set. And honestly, that is the core paradigm shift of machine learning. We are solving practical problems through examples rather than hard-coded instructions.
Now, machine learning comes in a few different flavors. You've got unsupervised learning, which just kind of hunts for hidden structures and completely unlabeled data. But for this explainer, we are laser-focused strictly on supervised learning. This means every single piece of data we collect already has a super clear, definitive label attached to it.
To totally demystify this whole thing, we're going to trace the journey of just one single piece of data, an email, through 4 sequential phases. By breaking the supervised learning process down into these actionable, concrete steps, you'll see exactly how human inputs turn into the machine intelligence running your daily inbox.
Phase 1. Data collection. Gathering the examples.
All right, let's lay the groundwork. If our problem is spam detection, our first real action is to gather a massive data set. Let's say 10,000 emails. But here's the absolutely crucial part. We have to manually assign a label to every single one of them. We literally go in and explicitly mark each email as either spam or not spam. You could sit there and do this yourself or pay someone else to do it. But regardless, this labeled data set is the absolute bedrock of supervised learning. The machine just cannot learn without these examples.
Phase 2. Data preparation. Making data machine readable.
Okay, so we've got our 10,000 labeled emails, but computers don't exactly read English text the way we do, right? To bridge that gap, data analysts use this clever little technique called a bag of words. Think of it like taking a giant dictionary of 20,000 alphabetically sorted English words. For just one single email, we create this massive 20,000 dimensional feature vector. So if the email contains the word A, boom, we put a 1 in that spot. If it doesn't contain the word Aaron, we put a 0. And we literally do this all the way down to the word Zulu. Then we repeat this exact same grinding procedure for every single one of our 10,000 emails.
But wait, we're not just translating words. We also have to translate our human-readable labels into actual numbers, which lets the machine process spam as a mathematical +1 and not spam as a -1. This specific numeric labeling is an absolute requirement for the learning algorithm we're going to look at next.
Phase 3. Model training. Drawing the line.
Now that our data is beautifully structured into numbers and feature vectors, we hit the most critical phase. The algorithm we're using here is called a support vector machine, or SVM for short. Imagine all 10,000 of those 20,000 dimensional feature vectors just floating around in a vast, high-dimensional space. To find the underlying pattern, the machine attempts to solve a massive optimization problem. Because, as the saying goes, machines are just exceptionally good at optimizing functions under constraints. To wrap our human brains around this geometrically, imagine squashing that insanely complex 20,000 dimensional space down to just 2 dimensions so we can actually picture it. The algorithm looks at the positive spam and negative non-spam examples and basically tries to draw a line, a hyperplane, or what we formally call a decision boundary. Its whole goal is to perfectly separate the positive spam examples from the negative ones.
But it doesn't just sketch any random line. The specific constraint the machine is trying to optimize is maximizing the margin. The margin is essentially the distance between the closest examples of the 2 classes. So the SVM explicitly forces that decision boundary to sit as far away from both clusters of data points as possible.
And here is the absolute game changer. That visual separation, it all boils down to a really simple mathematical equation. The equation of that perfect dividing line is just Wx minus b equals 0. Through the whole training process, the machine has actually found the optimal values for W and B. That final, simple little equation is your trained model. The heavy lifting is completely done. Phase 4. Prediction. Filtering the spam.
So we have our carefully calculated model, and this is where the pipeline actually goes to work for you. When a brand new email hits your inbox, we just run it through the exact same preparation process. We convert its text into a 20,000 dimensional feature vector, plug that vector right into our model's equation as x, multiply it by our trained w, subtract our trained b, and then we simply check the mathematical sign of the result. It's an incredibly elegant mechanic. If the result of that math is a positive number, a +1, our model predicts it's spam, and it tosses it straight into the junk folder. But if the result is a negative number, a -1, it predicts it's not spam, and it drops it safely right into your primary inbox.
Why it works. Trusting the math. Okay, so we've built this amazing pipeline, but why on earth should we trust this math to classify emails it has literally never seen before? Well, think about how that nice large margin safely separates the positive and negative subspaces. If our original 10,000 training examples were chosen well, a brand new spam email is statistically going to use similar words. Because of that, it will mathematically land in the exact same geometrical subspace as the older spam examples we trained it on. It just naturally falls on the correct side of the boundary.
And that loops us right back to why maximizing that margin was absolutely crucial during training. A larger margin directly contributes to better generalization for future examples. By intentionally finding the widest possible gap between classes, we shrink the chance of making errors when the model eventually encounters typical, everyday new data. We're essentially leaving plenty of wiggle room for slight variations in how an email is worded.
But I want to leave you with one final thought here. Our model's success completely relies on new data statistically resembling our original training examples. So what happens if the data environment totally shifts? Say spammers invent an entirely new vocabulary tomorrow that wasn't anywhere in our original 10,000 emails. How do we keep our carefully optimized models from just completely breaking down? It is a fundamental challenge in machine learning and definitely something to chew on. Thanks so much for joining me on this explainer, and hey, keep questioning the data.